I say is this triangle is a visual representation of those identities. Makes sense, right? I mean, it's a reasonable start. Now that you know that, that's where the problem, you have problems like kind of start there, right? And then where do you go from there? Well, Pythagorean theorem tells you this is what? 1 minus x squared, right? And goodness, once you have that, then it's easy. It's easy to write things down like sine theta. What's sine theta? Opposite, right? Over hypotenuse, which is 1. But on the other hand, this says that the sine, what is theta? Theta is sine of inverse cosine of x is equal to what? Square root of 1 minus x squared. So like there's how you do that kind of problem. And once you know this, other things like, say, cosecant of theta is kind of just silly, right? That's 1 over sine theta, which of course is then 1 over the square root of 1 minus x squared. Do you guys see the idea there? Do you want me to do another one, like tangent? Here, I'll throw in tangent. What's tangent theta? Opposite, yeah, the square root over x, right? So that would be the tangent of the inverse cosine of x. Now, the reason that this problem is important and that formula I just boxed is so nice is what we've done is we've traded this ugly formula in terms of tangents and inverse cosines for this rather simple algebraic expression, right? What's an algebraic expression, by the way? It's an expression you can build from algebra. Okay. In other words, it's constructed from a finite sequence of additions, subtractions, multiplications, roots, and divisions. That's it. If it's got logs or exponentials or sines or cosines, it's not an algebraic expression. It is a transcendental expression because it transcends algebra. Anyway. You guys have questions? Yes, sir.
Class tomorrow, the homework that you're going to assign for tomorrow, is that not due Monday now?
No, the homework which is due this week is due Monday.
Even Fridays?
Yeah, even Fridays. I just integration by parts.
Oh, okay.
Yeah.
I didn't know if that was the next section.
Yeah, that's the next section. Yes, sir.
I have a really stupid question.
Go for it.
It turned around in my head. What is inverse tangent of -1? Is that -3 pi over 4?
Inverse tangent of -1. Well, inverse tangent of x is defined for what? Tangent of inverse tangent of x is equal to x for what? Oh, I'm sorry, I got it the wrong way. Inverse tangent of tangent, I mean, the top one is not, this one is, I mean, good to go. There's no, no, inverse, the domain of inverse tangent is the range of the tangent, which is all reals. But the inverse tangent of tangent x is only x again for x what? Yeah. Right, so when you say, what's the inverse tangent of what did you say? -1, you gotta choose something from in there. Right, so you can kind of look at it. Slope -1's down here. Right, I mean, by the way, tangent theta. When we talk later about polar coordinates and such. So you can also think tangent theta is the slope of anyway, that's minus pi over 4 gives me that angle. So it's minus pi over 4. Yeah. I could push the homework back to Tuesday if it makes a big difference. It's not like the end of the world to me. That'd be helpful? I will do that. But it still includes integration by parts. Yes, sir. Which number?
7.732.
Oh, Now I know why we're doing the quotient rule. When I looked at it this morning, I removed the x from the numerator. Stop that. Stupid. Behave. So number 32 is this one. So it is somewhat troubling to me that you guys are asking about this problem, because it means that you don't have a very good background in Calculus 1. Which means, I mean, if you don't understand how to do this problem, you probably need to go and take a half hour and just work problems from like section 3.3 on the chain rule, or 3.4, back and back. Oh, where is it? Where are we? Back, way back. Need the way back machine here. Where's the chain rule? 3.5. I think if you don't understand how to do this problem, you probably need to go back and work a bunch of problems from section 3.5. I'll tell you how to do it, though. So, and also, so, I mean, how do you, before I get carried away, what's your actual question?
Well, I know how to do that.
Oh, okay. Good.
I mean, I get to a part and I can't finish it. That's all.
You don't know what to do with the c greater than 0, is it?
Yeah, probably that.
So, I mean, basically you use quotient rule, right? And also chain rule to do that. Now, for example, I'll just focus on the second piece. The first piece, there's probably most of you can do, but I think, well, I don't know. So this is 1 over the square root of 1 minus x over c quantity squared. Now, how do I know that? Well, we derived the derivative of inverse sine was 1 over the square root, right? And then I have to multiply by the derivative of the inside function, which gives me 1 over c, right? Because I have to multiply by the derivative of the inside function. Derivative of x over c is just 1 over c. Okay, so then I've got 1 over c times the square root of 1 minus x squared over c squared. Now here's the thing. If I have 3 times the square root of stuff, I can say that that's 9 times the square root of stuff, right? I can bring the 3 inside and make it 9. On the other hand, if I've got a minus 3 times stuff, square rooted, I have to say that's minus the square root of 9 times stuff, right? So what I'm trying to tell you is we can only bring the c inside the square root and make it a square if we know c is positive. And that's why they told you c was positive at the start of this problem, so that you can make this step. Right? So you said you can't get to the end. Do you mean like you found an answer online or something you're trying to match up with, or something like that? I mean, surely solution manuals exist for this book, but, or Wolfram Alpha, et cetera, I don't know. I'm as interested with the process as I am with the answer in here, of course, right? So, does that make sense? I mean, I don't know. I still don't know. I'm not sure what your question was. I'm just kind of cluster bombing the problem. But this is a kind of tough differentiation. I will say the quotient rule is kind of. Other questions? I'm sorry we haven't done more integration this week, by the way. Don't worry, I will fix that next week. It would be fun if we have class tomorrow, right? That'd be a thing. Yes, your question?
For number 50.
On which page? Or which section?
In the first section, 7.
Uh-huh.
What do you want to make your u? Do you want to make it e to the negative x?
Yeah, I think that'll do it.
Or e to the x?
e to the negative x, I think, is the way to go there. Now, the critical thing for that one, I've told some of you already, is, okay, so you let u equal e to the minus x, right?
Yeah.
On the one hand, you've got x equals natural log of 2, right? So that will change the bound to be u of the natural log of 2, right? Now that bound, u of natural log of 2, would be like e to the minus natural log of 2. But be careful. That's not minus 2. See, because this is e to the natural log of 1/2. And only e to the natural log of something just gives you back the thing inside, right? We can't ignore minuses and other numbers in front. Like exponential and natural log are inverse functions. Exponential and minus the natural log function are not inverse functions. So like the natural log of 2 bound changes to 1/2. The natural log of 3 bound changes to 1/3. And then it'll make sense, right? Because if you did it without doing that, you get like natural log minus 2. You're like, ah! It's bad. Other questions? I can probably speculate what u should be if you just ask me about the problem. Here, let me look at another one. Here, let me just try a generic quadratic. I'll show you something. I guess those of you who had homework questions have asked me them already, and those of you who don't, well, don't have questions. So, there's something I know that is an issue that we need to start thinking about, so I'll just go ahead and attack it right now. It's not really specifically an integration by parts thing, or it's more of a u substitution thing. Suppose I have something like dx over, I don't know, x squared plus 4x plus 5. How would you do that integral? Or more generically, here's a question. What can we always do with quadratic expressions? We can always complete the square, right? And 3 things will happen. Either you get the square minus a positive constant squared. You get the square minus a constant squared. You get something squared plus a constant squared, or you'll just get, it's already a perfect square. So what happens here? When I complete the square in the denominator, I have x plus 2 quantity squared plus what? Three is not going to do it. Let me work it out. X plus 2 quantity squared is what? X squared plus 4x plus 4. So not -1. It has to be 1, right? So we can say this is really the differential of x plus 2 divided by 1 plus x plus 2 quantity squared. And so that's the inverse tangent of x plus 2 plus a constant. I used sneaky notation here. Let me show you how you usually do this. Most of you have been taught to do this, right? This is really the integral of du over 1 plus u squared with what? U equal to x plus 2, right? And then eventually you'll get down to there. So this is very sneaky notation. This implicitly indicates that you're making a u substitution without actually ever saying u is equal to anything. Have you guys ever seen that notation? Here, I'm going to use it again on a simpler example. Integral of e to the x squared times 2x dx is the integral of e to the x squared times the differential of x squared. So this is e to the x squared plus a constant. This notation is very popular in Asian countries. It's It's part of why they can calculate faster. Also, numbers in Chinese are single syllable. We've got like 1, 2, 3, 4, 5, 6, 7. Oh, those are single syllable. They're shorter, though. They're like, I don't know, my wife says that counting in Chinese is easier. Also, you don't have dumb name for fish. Like, there's not like red snapper and tilapia. It's like yellowfish, redfish, bluefish. I mean, the naming is much better, yes. What's that? Oh, absolutely. Yes, I allow that. But you have to use it with understanding. So, okay, one other example. I think we're almost out of time. Or we're out of time, but I need to show you another example. Just one more, and then I'll stop. What if I had the integral of dx over, say, x squared, I'll make it kind of similar, 4x, and I want it to work out to -1 instead of 1. What do I do? +3. Okay, great. Thank you. This is the integral dx over x plus 2 quantity squared -1. So this is really the integral of du over u squared -1. And what is that? We learned that just a little bit ago, that the derivative of inverse hyperbolic tangent is what? Oh man, I erased it. I can't remember off the top of my head. Is it 1 over x squared -1, or is it 1 over 1 minus x squared? That's my question. So there's a minus here, right? So if you're faced with integration of something that's got a quadratic, remember you can complete the square to make it fit one of the things that we've already come into contact with this week, all right? I'll try to do a lot more of completing the square as we work examples next week. If you're uncomfortable with it, don't feel bad. Personally, I didn't really learn. Yeah, you can cut it off. Personally, I didn't really learn